You are given a tree and you start your journey at the root node of the tree at time is equal to t. At each stage of the journey, you have to descend into one of the children that is available. How do you decide which children to descend into? Assume that you arrived at this node at time is equal to m. Then you compute m modulo d, where d represents the number of children that you have. In this case, d would be equal to 3. Then you know that this m modulo d, it will give you a number that is strictly less than 3. Suppose it can give you anything between 0, 1 and 2. Then you can assume that the children are numbered from left to right. So this is the children 0, this is child 1 and this is child 2. So whatever the value of m modulo d comes out to be, you descend onto that child and then you repeat this process. But when you do this descent, you will take some time to reach the child. So this is this is a rooted tree, but it also has weights on the edges. So suppose this is W1, this is W2. This means that if you started your journey at this node at time is equal to t and you decided to descend over here, then when you reach over here, the time would be t plus w1 because it takes w1 amount of time to cross this edge. Similarly, when you reach this node, the time would be t plus w1 plus w2 because to cross this node, you take w1 time and to cross this edge, you take w2 time. And once you get this time, this will act as the m that I just talked about. M would be t plus w1 plus w2, and depending upon what the modulo of this m is, there will be a unique child to which you have to jump to from this node. So you continue your journey like that. Then you can see that the answer for a fixed time is unique. So if I fix the time, there is a unique sequence of steps that you have to follow and such that you finally arrive at a leaf node. So the problem asks you to find, given a series of t, like given several queries, suppose if I give you t1, t2, t3, t4 and so on, can you quickly tell me what is which leaf vertex would you reach when you start the journey at time t, and which leaf vertex would you reach when you start the journey at time t2? So in this video, we will explore some concepts related to number theory, which is basically this topic, congruence relations in number theory. And we'll also look at an offline query processing techniques, which is very useful in these kind of tree problems that do not require a live update to the tree values. There is no prerequisite for this video, and we'll first start out with this congruence relation. We'll take a quick refresher on this. I will not dive too much into this, although the things that we discussed in this congruence relation, it's not very difficult to grasp, but it is actually very useful to solve this tree related problem. So at first glance, these two might not even be related because sure, modulo is there, but then modulo appears in a lot of problems. So doesn't mean that just modulo is appearing over here. Somehow number theory and congruence relations will creep in. But you will see a beautiful application of congruence relation to simplify this tree problem. So first we'll start out with defining what a congruence relation is, and then we'll look at some properties that we want to reuse in this tree problem. So let's start by defining congruence relations. Let's consider any number x and let's look at x modulo 4. Now you know that x modulo 4, what are the possible values it can take? It is 0, 1, 2 and 3. So let's fix one of these values and let's say x modulo 4 is equal to 3. And we want to analyze what are the numbers that produce a modulo 3 with 4. So what are the set of numbers that produce a remainder 3 when divided by 4? Now, what is the smallest number that you can think of? That is of course 3. What is the second smallest number? So if you are not able to deduce that, you might remember Euclid's division lemma, which says that x can be written as p into the, it can be written as x is equal to divisor into quotient plus remainder. So the remainder is 3 and the divisor is 4. So this means that all x can be written in this format where q can be any integer. So that's why the first number would be 3, second number would be 3 plus 4 which is 7, third number would be 7 plus 4 which is 11, and then 15 and so on. So these are the set of x that are congruent to 3. So you can say 3 modulo 4 is equal to 3, but 7 modulo 4 is also equal to 3. Now notice that in the modulo 4 world that we are dealing with, numbers greater than 3, they do not exist at all. There are only 4 numbers in this world. This means that what would 7 and what would 11 look like in this world? So for all practical purposes, you can say that 3 and 7 have basically no difference between them. They are essentially identical. Why? Because they produce the same modulo when divided by 4. This means you can say that 3 is equal to 7. But in what world? So for that you define a notation. You say 3 is equal to 7, but this time we are adding a new notation for equal because 3 cannot be equal to 7 without a context. And the context is that we are saying that 3 is equal to 7 in the world where you treat all numbers modulo 4. Similarly, 3 is also equal to 11 in this same world modulo 4. 3 is also equal to 15 modulo 4. Why? Because all of these numbers produce modulo 3 and 3 also produces modulo 3, so they will be equal. But when we write this notation, we don't really call this as an equal sign. We say that 3 is congruent to 15. So this is known as congruent. So 3 is congruent to 15. But what is the benefit of writing it in this manner when we could have just said that x modulo 4 is equal to 3? So you will see some of the benefits. So the benefits are, right now we had fixed this r is equal to 3 and we were saying that 4 is congruent to r, and then no, we were saying that 7 is congruent to 3, 11 is also congruent to 3, 15 is also congruent to 3, and all of them are happening modulo 4. This means that since you have defined this congruence relation on two integers, you can now treat it like, so arithmetic would now be possible on it. So first of all, it's not at all obvious why arithmetic is obvious on it. But if you do some verification on paper, you will realize that if A is congruent to B and A is also congruent to C, you can see that B and C are also congruent to each other. But why are these mathematics actually working? So we'll just quickly talk about them, but not dive too much deep into them because they are very standard techniques. But the basic idea is this, that we started out with the remainder concept. That is, when you divide x with 4, the remainder is 3. But handling the remainders is a bit tricky. So let's start with this formulation. If A is congruent to B modulo M, right? This essentially means that A and B are equal. For all practical purposes, they are equal in the world where every number is treated modulo M. Then you can see that A minus B, you can actually perform arithmetic by bringing this on the left hand side. You can see that A minus B is congruent to 0. Now, why is this allowed? Because they produce the same remainder modulo M. So if you subtract that same remainder, you would get 0. So it's actually not obvious why you can bring it around, but with this explanation that remainder and remainder cancel out to produce 0, then you can explain that yes, they are, their difference is indeed congruent to 0. But how does this fact help us? Because with this fact, you can prove a lot of other theorems that are related to congruency. That is, this time we are saying that A is congruent to B, and we are not even talking about remainders anymore. We are saying that A is congruent to B in any world of M if and only if their difference is congruent to 0. But what is actually 0? So 0 means in this world, which numbers produce a remainder 0 when divided by M? That would simply be multiples of M, right? Only M, 2M, 3M, etc. Only these numbers can produce 0. This means that you can reword it and say that A is congruent to B if and only if their difference A minus B is a multiple of M. Is a multiple of M. So with this understanding, you can now see that if A and B are congruent, if A and B are congruent and B and C are congruent, then A and C will also be congruent. Why? Because if A minus B is a multiple of this and B minus C is also a multiple of this, so A minus C you can get by adding those two together and they will still remain a multiple. This means that you can now group certain elements. You can now group certain elements and you can call them as equal, even though they might not look like equal, but they are essentially equal. So this grouping that we saw over here of 3, 7, 5, 11, 15, this means that for this grouping, you will see that if you consider the world of modulo 4, then in this world 3, 7, 3, 7, 11, 15, all of them are essentially equal. There is actually no difference at all between 3 versus 7 versus 11 versus 15 and so on. So that's why we say that all the elements in this group are congruent to each other. they are congruent to each other. Or in other words, you can say that if they are congruent to each other, it means that they produce the same remainder when divided by 4. So in mathematical terms, it's known as producing the same residue class. So it produces the same residue class when divided by m. Now all of these might look very trivial, but you will see how powerful these interpretations are for solving various competitive programming problems. Now let us look at some more relations on these congruence. So first we'll explore this part. So let's start with two numbers, and let's say that these two numbers are identical in some world m, right? They are congruent in some world decided by m. This means that their remainders are same, or in other words, their difference divides m. Now, can you find any smaller world in which these two numbers will still be the same? For example, in the modulo 4 world, you can see that in the modulo 4 world, 3, 7, 11 and 15, they are considered practically the same number. But is there any smaller world in which these are also considered practically the same number? Yes, that world is modulo 2. Why? Because in the modulo 2 world, all of them produce the modulo 1. Therefore, since all of them produce the same modulo, all of them are equal to each other. So can you generalize this statement? So what is the relation between 4 and 2? What can you guess? So you can see that it is actually a divisor. So this gives us a hint that we should explore the divisors of m and see can we infer something about the divisors. Now if a and b are equal in the modulo world of m, let's see if they will be equal in the divisor world. So will a be congruent to b modulo d, where d is the divisor of m? So the answer is yes, it would be, because when is a congruent to b? We had already concluded that this means that a minus b is congruent to 0. But when is a minus b congruent to 0? This can only happen when a minus b is a multiple of m. So a minus b is the multiple of m. But if a minus b is a multiple of m, you can write it something like a minus b is equal to k into m. But if d is a divisor of m, you could rewrite this expression as a minus b is equal to k into, let's write d over here, and to accommodate for this, we write m over d over here. Now you see that this and this two are practically the same because their value turns out to be k into m, and we can actually do this division because divisors exist in pair. If d is a divisor, m by d is also an integer and also a divisor. This means that a minus b also follows that same pattern where it has some number into that divisor. It means that a minus b is actually a multiple of the divisor as well. It means that if you start with a bigger world of m and two numbers are equal in that big world, they will also be equal in this small world. So this is one fact that we will use in the later parts of this video, so hold on to it. Now let's talk about another interesting observation for this. This time assume that A and B, they are two numbers, they are equal in the world of M. So A is congruent to B in the world of M, and assume that they are also equal in the world of N. So you see that you started with two small world. Now can you find me a bigger world where they would still be equal? For example, let's consider 6, or let's consider this. If A and B are equal in the world of 2 and they are also equal in the world of 3, which bigger world would you think they would also be equal in? So notice that if they are equal in this world of M and they are equal in this world of N, what does this mean? We said that A is equal to B or A is congruent to B if and only if their difference is a multiple of M. So A minus B must be A minus B is a multiple of M. But A minus B should also be a multiple of N because they are equal or congruent in both the worlds. This means that A minus B is a common multiple of M comma N. A minus B is a common multiple. Therefore, you can say that if you consider the world where you have the smallest common multiple, which is nothing but the LCM, if you have this world, LCM of M comma N, then A and B will still be congruent in this world. So this world is of course bigger than LCM. So this world LCM of M comma N is bigger than this and bigger than this. So it will also be equal. So these two numbers, they will also be equal to each other in these smaller world, but then also their combination of a bigger world, which is the LCM. Now of course there could be other bigger worlds as well in which they would be equal, but this is one world where they have to be equal. Now what is so interesting about this? So the interesting part is that we said that if they are equal in this smaller world, then they have to be equal in this bigger world of LCM. But actually, and this is the more interesting part, the other way around is also true using the techniques that we have already discussed. That is, if I tell you that A is congruent to B in a world of LCM of M comma N, then you can actually infer two things from this. That is, the first thing that you can infer that if you switch to a smaller world, then A will still be congruent to B in the world of M and A will still be congruent to B in the world of N. Why is this fact true? Because of this part that we just had discussed, right? That is, whenever you switch to a smaller world from a big world, if the smaller world that you are switching to, if that is a divisor of M, then that congruence relation still holds. But notice that LCM of M comma N, M always divides its LCM because by definition it is the lowest common multiple of M. So M of course will divide it, but N will also divide it. This means that you have a bidirectional mapping between them. So this implies this, but then this also implies this trivially. So how does this help us? So now you will realize that we are now, if I tell you this fact, if I tell you these two equations, you can infer this. But if I tell you this, you can infer this as well. So this means that in competitive programming problems, you are always looking for ways to encode some information so that you don't have to iterate over them again and again. For example, in binary search or in prefix sum, you encode some information. Like, how do you do prefix sum? You encode the entire sum over here so that you can quickly compute this subarray sum by computing this sum and subtracting them. But now we are seeing a similar technique where we are able to encode two separate information into one information. So I don't have to maintain two equivalence classes, or I don't have to maintain two congruence relations anymore. I can just say one statement and be done with it. And that statement is that A and B should be congruent to B in the world of LCM. In fact, you can even extend this analogy even further, because you can simply apply induction over here to say that if A is congruent to B in the world of M1, or let's say in the world of N1, and it is also congruent to B in the world of N2, and it is also congruent to B in the world of N3, and also in the world of N4, then instead of carrying these four information around, which is basically O of n conditions that you have to maintain, you can simply maintain an O of one condition by simply saying one statement that encodes every information possible. And that statement is that A is congruent to B in the world of LCM of N1, N2, N3, and N4. Just saying this indirectly says this as well. And saying these four statements indirectly says this statement as well. So why don't we just track one statement? Now you will realize that if these numbers, so you will realize that LCM is nothing but product of all the numbers divided by their GCDs. So product of all these numbers divided by GCD of N1, N2, N3, and N4. Therefore, if all of these numbers N1, N2, N3, and N4, if they are coprime, then their GCD would be 1 and LCM could be replaced by their product. And this thing that you see on the screen, where all the NIs are coprime, and then you are looking for something, you are looking to encode that information using their product. This is nothing but the Chinese remainder theorem, because this is the setting of the Chinese remainder theorem, where they give you two numbers that are equal in n different world from n1, n2, n3, n4, and they want you to find out like what happens to those numbers in the product world. And why does Chinese remainder theorem work? Because I mean, no, not talking about why does it work, but like why does its setting work? Because of this thing only. Like we always assume that LCM, in the LCM world, they will still be equal, but in the CRT case, we assume that all of these numbers are coprime, and then this LCM gets switched to product because their GCD is 1. But that is a divergence, but it will not be applicable over here, because in this problem, these series of equations that you will see, they will not actually be coprime. So you won't be able to directly apply CRT over here. And in fact, CRT is not a prerequisite to this video. If you just understand this LCM concept, you should still be able to solve this problem. So, okay, let's quickly summarize what all things we have gained so far. So first of all, we concluded that if something is equal, if two quantities are equal in a bigger world, then they will also be in a smaller world if you curate the smaller world carefully by picking a divisor. This was one thing. And then we said that if two numbers are identical in two smaller worlds, then they will also be identical in a bigger world, and that bigger world is the LCM of these two numbers. In fact, we said that this is not just necessary but also sufficient, meaning that if you just say this statement, then you don't need to repeat these statements. Therefore, if you want to maintain congruence relation on a series of worlds from n1, n2, n3 and n4, you could just say that A and B are actually congruent in the world of LCM of n1, n2, n3 and n4. So this is the second thing that we had learned. The third thing that we had learned is that if A is congruent to R and B is also congruent to R, then A and B are essentially congruent to each other. This means that there is no difference between them. And now you can say that why is this powerful? Because you are able to completely remove the middleman R from the picture, and you can directly claim that two integers are equal without even knowing what this R is. Now let's look at some other properties. So consider x modulo 4. You can see that the answer is of course 0, 1, 2, 3. But if x itself is less than 4, then you can see that x modulo 4 is equal to x, right? Therefore, you can say that in your real world, where you are not dealing with any modulo and stuff, if you have n integers, let's say if you have n distinct integers, if you have n distinct integers in an array a1, a2, a3 up to an, then you can say that in what world will they not be equal to each other. So right now, if you do not take any modulo, of course they are not equal to each other because they are distinct. But if you wanted to find a modular world in which they are not equal to each other, what is the simplest world that you could pick? If you pick this, m is equal to max of ai plus 1. In this world, you can see that two numbers cannot be equal to each other. Why? Because ai modulo m would be equal to ai, and therefore, since none of the ai's are equal to each other, then their remainder also cannot be equal. So this means that if you want to split, so this element, if you want to split it into groups of one where nobody is equal to each other, like if you want to split it into groups where each element, where all the elements in a group are congruent to each other, then if you want to add only one element to the group, you can smartly select your m as the maximum element plus 1. And then if you really had distinct integers, then each group will only contain one integer only. But now, what if I ask you to choose a modulo where all the integers are essentially congruent to each other? So if you have n distinct integers, how do you make them equal to each other? In what world? So can you smartly pick the m? So in what world 1, 2, 5, 9 and 13 and 22? In what world are they actually equal? So it's not the even world, it's also not the odd world. So what is it? So if you see that if you pick m as 1, then in this world where every number is treated as modulo 1, then there is in this world only one number exists. What is that? 0. So all of these numbers actually have remainder 0 when you divide it by 1. So in the world of 1, all these elements are actually equal. They actually go into one bucket. So you can see that on the extreme end, you have one where all the elements are essentially in one bucket, and then you have max of ai plus 1 where all the elements are in a different bucket and none of the elements are identical to or congruent to each other. So you will see how these interpretations will help us in the tree problem. Now, let us look at the problem that we briefly discussed at the start of the video. So You want to start your journey at the root node T, and at each node, suppose you have arrived over here and the current time shows M. Then of course you have to take M modulo D. This will give you one of the child, and then you have to move towards that child. And how much time will you take to reach that child? That would be W time. So by the time you arrive over here, the time on the clock would say M plus W, where M is already not equal to T because you must have spent some time to reach this vertex. So how do we solve this very complicated, very difficult problem? At first glance it looks to be difficult, but you'll see that this solution is hardly 15 to 20 lines of code. Now let's focus on one node. Suppose I am dealing with this node over here. Then if you start with any particular T, then if that journey eventually reaches here, then what does it mean? It can only reach here from its parent, and it can only reach here from its parent, and it can only reach here from its parent. It means that if a query reaches a node, then there is a unique path to it. And if there is a unique path and I know that the starting time is T, can you say that there is also a unique time at which you arrive at this vertex? Yes, because if there is a unique path, there has to be a unique time, because the time is nothing but T plus summation of the weights that you see on your journey. But can you quickly find out what is this unique time will be for each vertex? So you see that you can only arrive at this vertex from a unique path from root, but then there is already a unique path from root, and the vertices and the edges in that unique path is already decided beforehand. So in fact, this time would be nothing but T plus distance of u, because distance of u means sum of weights of all the edges from root to this node. So T plus distance of u would be the time at which you arrive at this node. Now notice that you have several queries. It's not just a single T. You have T1, T2, T3 and so on up to T of Q. But since there are no updates on the tree, there is no compulsion for you to read one query and then answer it, since this is not an interactive problem. So you can actually store all the queries and then you can start doing a DFS with all the queries at once, and this is known as offline query processing. Now, why would this work? It's because we just said that any T, if you fix a T, there is a unique path. And that is exactly what the problem is asking you to find. They are saying that for each Ti, tell me which unique leaf vertex would you visit. If that is the case, then if you were to start your journey from here with all the Q vertices in a single array, then when you do this split, you can see that some of the TIs will go over here and some of them will go over here, but they are actually disjoint. So one TI cannot go to two branches because they are completely disjoint, because each TI follows a unique path. A bunch of TIs might go over here and a bunch of them might go over here, but that's just about it. There will be no overlap between them. So this means you can just do a regular DFS and you can decide, okay, you start with this big bucket over here and then you figure out what is your time right now. Your time would be T, the original time, plus the distance of the current vertex, and then you decide which elements of the bucket goes where. So you compute M modulo D, and all the elements would go to the child at this index, where you can say R is equal to M modulo D, and all the elements would go at this location. Now you can see that when a bucket arrives over here, we are saying that this entire bucket goes to just one children only. So is it not possible that from this node it something goes here and something goes here? Yes, that is possible, because we are saying that if you fix m, only then all the buckets, if you fix m, basically if you fix the ti, only then that element of the bucket will go to this children, but all the other elements will go to other children. So if t is fixed, then going to this child is already predetermined, but if it is not fixed, then of course somebody would go here, somebody would go here. So let us first look at a simple implementation of this idea. So of course it would not get you an AC, because it is O of n square, because at each stage, at each node, you will be inspecting the buckets to see which of the bucket elements should be sent to this node and which of the bucket elements should be sent to this node. But either way, let's look at the implementation. So you start with the bucket, and your initial bucket would be the entire array, entire query array in this root node. And then you check if it is a leaf node, then you know that you have arrived at a unique leaf node. So you know that all the queries that eventually arrived here, they must have gone through a unique path and then finally arrived over here. It means that this leaf node is the answer to all of those queries. So you can simply print that answer and return. Otherwise, if you are at this node, you find out how many children that it has by looking at what is the size of the adjacency list, and then you compute what is the time that you have. So if you started your journey at ti, then your current time would be ti plus distance of u. So this is the current time, and with the current time, if you take the modulo d, you can figure out which, so you can figure out which bucket will this ti go in, or which child will this ti go in. So you create a bucket for that child. At this child position, you push back this index. So this child will receive more than one element, but what will be the common thing amongst them? That all of them will have the same remainder modulo d. And then you simply run a DFS, and eventually you'll get your answer. So this approach works, and the time complexity is O of n square. So now what we are looking for is how to optimize the time complexity of this bucketing strategy, so that we don't have to do expensive work. Now what is the expensive work? You can see that the expensive work is iterating through each element of the bucket and then dividing it into smaller buckets over here, right? We figure out the time, and then we figure out which direction it goes into. So now we'll see some techniques from the congruence relation world, and we can see how having some formal definitions will help us simplify this thing. So let's start with this part. And suppose you have started with a bucket containing all the elements. And let's see how modular or modular arithmetic or the congruence world actually fits into it. Now suppose you arrive at this node at some point in your journey. Suppose this is node u, and you have arrived at this node at some point in your journey. How can you arrive at this node? Only from its parent, which is this node. But when you were at this parent node, what would the time have been? Suppose that time was m. Then if the time was m, then this node, if it is redirecting that all the ti's to this node, then m modulo d, and you know that m will be unique, right? M will be unique if your ti is fixed. So you see that if the time is m at this node, or if you don't want to treat it as m, which is unknown, then you can say something like, first let's treat it as m, and we say that if m modulo d is equal to the index, suppose this index is equal to r. So if m modulo d is equal to this r, then that element from this bucket would have been sent over here. But what is the interpretation of this? So this means that when M is divided by D, it leaves a remainder of R. But we had said earlier that you can remove the concept of remainder and you can simply say that in the world of D, M is actually equal to R in the world of D, mod D. Right? We had said that you can express this equivalently as saying that M is congruent to R, which essentially means that M is equal to R for all practical reasons. But this M is still unknown, right? We are only talking about the query times. But then what is the query times? So that is M would be nothing but Ti plus, let's say this is the node P. It is the parent, that's why I'm calling it as node P. So you can say that M would be nothing but Ti plus distance of P. This should be equal to R. Now notice that this R is unknown because for each child will have a different R, right? This is 0, this is 1, this is 2 and so on. But now notice that you can actually do arithmetic on this because this distance of P is fixed. So you can write it equivalently as Ti is actually congruent to R minus distance of P. And let's consider this value as R prime because this would be fixed because we are investigating this node and this would also be fixed. So we can write it like so. Ti is congruent to R prime in this modular world of D. Now remember when we were discussing this congruence part, we had emphasized on one fact that if A is congruent to R, if A is congruent to R and B is also congruent to R, then even without knowing what R is, you can simply say that A and B are equal to each other. That is, they are identical, they are congruent. So here you can see that in the modular D world, all the TIs, and this time we have actually removed all the distance and stuff, right? We have moved them to the right hand side. So if you look at the original array, then if you look at this original array in this world, in modular D world, then all the TIs which are equal to R prime in this world will arrive over here. There might be some blocks ahead, like on top of it, that we'll talk about later. But what are the only candidates? I mean, candidates cannot come outside this list, right? It has to be a subset of this list. But now you can see that you can actually remove this R prime from the picture, and you can see that in this modular D world, all the TIs which are equal to TJ, they will form one bucket and only that bucket can arrive over here. So you see how smartly we removed R from the picture altogether, and we said that you start with this array and you consider it modulo D. D is known to us because D is the number of child that this node has. Then you split it into several groups, right? And in each group, all the elements will be equal to each other. Why? Because their modulo is either 0 or 1 or 2 or 3 and so on. So whatever their modulo is, I don't care, right? Because whatever their modulo is, that will exactly be equal to R prime. But I don't care about R prime. What I care is that whatever happens to this element, the same thing will happen to this element as well. Because if at this node, if you had this bucket and if you took modulo D, it will split it into several smaller buckets, right? It will split it into several smaller buckets. Now you can see that all the buckets would behave in the same manner because they are essentially equal to each other. So they will be transferred over here and so on. So what can we conclude from this? That this relation is true, that is all the elements that are equal to each other in the modular world of D, if Ti is equal to Tj, they are part of one single bucket, and only those elements will be allowed to pass through this node to this node. Now that is actually true both ways around. So if you if you take this as an example, you can see that for an element to arrive over here, right, this is the first level that an element will arrive at. It starts from here. So at the start, all the elements arrive at the same bucket. Now when an element reaches here, you can see that only those elements can reach here whose modulo 6, because there are 6 elements whose modulo 6 is equal to 2. Only those elements can reach over here. This means that only those elements which are actually equal to 2 can reach over here, which also means that only those elements which are equal to each other, right, only those elements which are equal to congruent to each other in the world of modulo 6, only those elements which are equal to each other have the possibility of reaching over here. So that's why the bucket that this receives, that will be a uniform bucket wherein each element will actually be equal to each other in that world. So if you are looking at the world of 6, then all the elements that you receive over here, they will actually be equal to each other. But now suppose after this you have received, you want to transfer it over here, right? You want to transfer it to 4. Then you can see that at this node only those bucket was received where all the elements in this bucket were actually equal if you were looking from the perspective of the world of 6. But when you send it down to one of this child, then this child will also follow that property locally. That is, whatever is received over here, they will actually be equal in the world of 4. So if you receive, let's say, Ti and Tj, then it means that Ti must have been congruent to 1 modulo 4 and Tj must have also been congruent to 1 modulo 4. It means that Ti must have been congruent to Tj modulo 4. But if this bucket came from here and this came from here, and here we are saying that these Ti and Tj were already equal in the world of 6, but now we are saying that they are also equal in the world of 4. So how do we encode this information so that we don't have to remember what all worlds they are equal in, right? Because you could have traveled a long journey over here. And that is where the concept of LCM comes in. Because remember, we had said that we are always looking for encoding some information in just one single congruence relation. So here you can see that so from the first node, at the first node only those elements in the bucket will be allowed to pass through that have the same modulo. But then everything here is same, right? Everything is here is same, but then you are doing some filtering again, and then you are saying that after this filtering in this other world, and this other world could be of 6 or it could be of 4, all the elements that are still remaining equal in this bucket, they should move downwards. So how do you encode this information? Now you can see that if you consider this tree, let's say if you consider this tree, then if you have taken this journey, if you have taken this journey and you have arrived over here, what can you conclude? You can see that only first you started out with the entire bucket, and then only those elements will be allowed to pass over here in which all the elements of the bucket are actually equal modulo 2, and then only those elements will be allowed to pass over here in which all the elements are actually equal modulo 2, and then actually equal modulo 1, and then actually equal modulo 1, and then actually equal modulo 2, and so on. So this means that you have a series of congruence relation. That is, uh, if Ti and Tj has arrived at this node, let's say Ti and Tj have arrived, so you can say that Ti and Tj must have been congruent to each other at each stage of the journey. This means that Ti and Tj are equal in the world of D1 that you saw earlier, and in the world of D2, and in the world of D3, and in the world of D4, and so on. So now, instead of remembering all of these information that Ti and Tj were equal to so many, were equal to each other in so many worlds, we can just remember one information, and that is Ti is congruent to Tj in the world of LCM of all the elements that we have seen so far. Why? Because we had said that this actually implies surprisingly both ways, that if they are equal in D1 and D2, they will also be equal in LCM of D1, D2, but the other way around is also true. So we can hide this information over here. So we just say that if two elements of the original array, if they are equal modulo this LCM, then you store them in one bucket and then you simply transfer this bucket. But how does this actually help us, right? So remember that we are doing some batch processing, offline query processing, and we wanted to avoid looking inside of that bucket. So how can we do that? Now, so let's see how we can do that. Let's assume that you start with this. Let's assume that you start with this. Now, whatever bucket arrives over here, all the elements in this bucket will be equal in the modular world of 6. And then whatever arrives over here, all these elements would be equal in the modular world of 4, but then they would also be equal to each other in the modular world of 6. In fact, you can say that all the elements that arrive over here, they will be equal to each other in the modular world of 12. And now the real optimization starts. Now you can see that if you are confident that all the elements that arrive over here, they are equal to each other in the world of 12, because we just have to maintain one number. We now don't need to maintain a series. So if all the buckets are equal in the world of 12, then if you have several child, let's say if you have 2 child, or let's say you have 4 child for this, then this time you can actually transfer this bucket simply down to the child that it goes to. Because if all the elements are equal in the world of 2, remember that we had discussed that you can go from a big world to a small world, right? If A and B are equal to mod M, then they will also be equal in the smaller world of divisors. This means that if the number of children that you have right now, if the number of children that you have is D, and suppose the number that you are storing currently, which is the LCM, right? So let's say that M is the LCM of all the DIs that you have seen so far, right? Which is all the DIs, let's say over I. Okay. So if M is the LCM, then you can see that if D divides M, if D divides M, it means that you are claiming that two numbers are equal in a bigger world, and you know that all the numbers inside the box are equal, right? Because one node can only accept equal elements only. So you are saying that two numbers are equal in a bigger world, and I want to jump to a smaller world where that smaller world is my divisor. Then even without looking into whatever is present in this box, because the number of elements in this box could be very large, you could simply say that all these elements, they will simply go to a single child only. Why? Because all of them would be equal. And since all of them would be equal, wherever the first node is going, wherever the first Ti is going, all the elements will go over there. So this means you can simply swap the array. You can simply send this array down without looking into that element. So here you receive that element. Here you receive an element. Here you receive a bucket that can contain a lot of elements. And then if you see, then you see what is the LCM of all the DIs that you have seen so far. And if the number of child that you have, that is your divisor, it means that you are jumping from bigger world to a smaller world, where the smaller world is your divisor. And in that case, you don't actually have to guess. You don't actually have to look. You can simply say that if all these numbers are equal to each other in this bigger world, they will also be equal to each other in the smaller world. So why don't I simply send this bucket? Why don't I just pass this reference to this smaller child? In this way, you don't actually have to look into that bucket anymore. So, okay, this looks like it would help, but here we are actually relying on the fact that this how much lucky we could get, right? We are only relying on the fact that if you are at this location, then we are saying that this LCM, it should be so lucky that the number of child should divide it. Otherwise, if it doesn't divide it, then of course you have to again split it into several smaller buckets, and you have to send it down to each child, right? And for each child, they will receive LCM of whatever the M is currently and whatever the D is currently. So you might think that this is a very minor optimization that depends on luck. Like sometimes we might get lucky and we might not have to look into that bucket, and sometimes we might do some worst case scenario and actually have to look into the bucket each time. So now this is where the like number theory and the tree part of this video ends, and now we will look at a different optimization technique, which is not really an optimization, you could say, because if you just implement this idea hoping to get lucky, you will actually get lucky and you will get an AC. You can even try coding this out right now. You will get an AC on this problem, but it's not trivial to see why would you get an AC, and in the remaining part of this video we'll show you how just applying this strategy and hoping that whatever the number of children that you have, right, hoping that this divides the LCM, and in that manner you don't have to look into this bucket every time. This hoping strategy will actually work. So let's see how many times we will actually have to look into the bucket and how many times we can simply do the transfer, right? But before we do that, let's look at before we do that, so if you have this tree, then you can see that you are starting out with a very big bucket. And what is the invariant that we are trying to maintain? What is the invariant? So the invariant is that whenever a bucket lands on this node, all the elements of the bucket are actually equal if you look at from the perspective of a clever world. And the simplest of that is D, of course, but then another fancy is LCM of all the DIs that you have encountered so far. So what is like, is that invariant really followed in this world? Like when you start from root? Actually, yes, because in the query you are given several TIs, right? TA, let's say T1, T2, T3, up to T of Q. So in which world are they equal? So you can see that they are equal in the world of M is equal to 1, because in this modular world every number is equal to each other because every number gives a division of 0. And then you split it down, so some elements will have modulo 0 when divided by 2, so those elements are practically equal to each other, and some elements will have modulo 1 when divided by 2, those elements are practically equal to each other, and you send them down this branch and then you send them down this branch, right? Now let's see what happens on this node. At this node you want to send down this node over here and here. So what is the D value of this node? That is also equal to 2. Then you can see that this bucket came from this parent, and in this bucket all the elements are actually equal to 2, right? So instead of maintaining M, when you reach this node you maintain M is equal to LCM of 1 comma 2, so you maintain M is equal to 2. So M always represent what is the world in which all the elements of the bucket are equal. So here all the elements of the bucket are equal in the world of 2, but then it has 2 child. Then if you take modulo 2, right, if you take the ti's as modulo 2, then they would still remain equal in this world, because they were equal in the world of 2, and you are again wondering what will happen if you take the modulo 2. Of course it will be equal. So you could simply transfer it either to this end or to this end. How will that be decided? That will of course be decided based upon the distance of you that you have covered so far. But whatever be the case, it can only go to one node. So the entire bucket, let's say, lands over here. Now again the invariant over here is that when this bucket arrives at this node, all the elements are actually equal in the world of m is equal to LCM of 1 comma 2, 1 comma 2 comma 2. Then now you want to split this bucket, because you want to figure out, okay, all of these elements produce the same remainder when divided by 2, but now I want to divide by 3. So okay, this time you do the brute force way. You simply iterate through each element of the bucket and then you divide them by 3. So the remainder could either be 0, remainder could either be 1, remainder could either be 2, right? And if the remainder is 0, you push that bucket down to here. Remainder is 1, you push that bucket down to here. Remainder is 2, you push that bucket down to here. But also you don't want to forget that information, that this bucket is split into several smaller bucket, but the bigger bucket originated from like all identical elements, right? So you have to preserve that information. So when you are pushing this bucket down over here, you could say that sure, all of these elements are identical in the world of 3, but they were also identical in the world of 2. So you could say that this bucket has the invariant of LCM is equal to 1 comma 2 comma 2 comma 3. So all the information you are encoding in just one single variable, so that this bucket can be pushed down even further. Now you see that when you arrive at this node, you don't actually have to look inside the bucket, because it contains 2 child only. So the modulo 2 would be the same for all the elements in this bucket. So you simply calculate the answer for the first child and move this entire array down via reference. Then again, if you encounter three elements over here, even in that case you don't have to worry, because all the elements are already equal in the world of LCM of 2 comma 3. So of course they will also be equal in the world of 3. This means that you just push it down. So now the final part of this video, where we talk about why this strategy that looks like it will not work in the worst case is actually correct, and actually the time complexity is not n square as we are thinking. So notice that, what is the time complexity? What do we actually mean by time complexity? So time complexity is just the total amount of work that you are doing, right? Now, if I told you to do this swap at every stage, swap at every node, like you don't look inside the node, suppose you got lucky at every node and you are doing the swap at each node. In that case, what would the time complexity be? So since you at each node, since you did not look at any bucket elements, you simply transferred that from here to here to here to here and so on. You are just doing a DFS on the tree, so the overall time complexity would be O of n. So what is actually increasing the time complexity? When you are actually looking inside the bucket. So when you are looking inside the bucket, we have already said that this bucket will come with an invariant m, which says that all the elements are actually equal in the world of m, where m will be the LCM of all the di's that you have seen so far. So this means that either you get lucky and this d divides m, then you are lucky, you can simply transfer this bucket to one of this child. Or if you do not get lucky, then you will investigate all the elements of this bucket and you will create several smaller buckets for these. But then what is the m value that you would create? Because you see that if m does not divide d, then so far you have known that all these elements are equal in the world of m, but they also have to be equal in the world of d, and you want to retain both this information. So you want to say that this, if m does not divide the d, then the next bucket will have this as m, right? This as the m prime, which is the LCM of m comma d. But if one number does not divide the other number, then you know that the LCM will be strictly greater than 2 into m, right? Or let's say LCM is strictly greater than m, so it will be greater than or equal to 2 into m. So it will be at least twice the current value. So this means that how many times will you actually be unlucky? It will not be that much before that LCM becomes infinity. Why? Because even if you start with m is equal to 1, even if you start something like this, at the root node m is equal to 1, then if you encounter 2, of course you have to look into all the bucket elements, sure. Then you might encounter, let's say, 3. So of course you have to look at all the bucket elements, but then L then the LCM would become 6. Then if you encounter 2, you are good, you don't have to look. If you encounter 3, you are good. If you encounter 6, you are good. But if you encounter 7, then again you have to look into all the elements, but this time the LCM will actually become 42. So you see that at each stage, every time you get unlucky, the LCM actually doubles, at least doubles. It could be even more, but at least doubles. So soon LCM will become so big that if you had T1, T2, T3 up to T of Q, and let's say all of these numbers are up to 10 to the power 18, then you can see that in just 60 steps, if you get unlucky only 60 times, then the LCM will become strictly greater than 10 to the power 18. And then we had already discussed this fact that if you take this m as the maximum element plus 1, then in that world all the numbers are not equal. So none of the numbers can be equal unless they were actually copies of it, like 2, 2, 2, etc. So this means that as soon as your LCM becomes greater than 10 to the power 18, there can be no further splitting. Why? Because at this point you can be sure that after 10 to the power 18, we are saying that all the TIs are equal in the world that is greater than 10 to the power 18. But then 10 to the power 18 is the max value of a TI. It means we are indirectly saying that all the TIs are actually equal to each other. This means that after this you don't actually have to peek into the buckets. So after you got unlucky 60 times, the next time you could simply transfer this bucket around. So you just have to track whether the LCM is greater than 10 to the power 18. If it is greater than 10 to the power 18, you can be damn sure that your entire bucket contains of identical copies of a single element only. So think about this fact, why this is true. And if it is not, if it has not grown to 10 to the power 18, then you are simply not doing any work, right? You are simply transferring. But then when you are actually doing the work, you are looking into the bucket elements and then you are splitting it, right? But then the next time you look into it, it will be at least double its size, so m will grow very quickly. So if you want some more rigorous explanation of why the total amount of work that you would do would not be much, so let's look at it. So suppose if you want to find out, let's say if you have this T1, T2, T3, T4 and T5, then the total amount of work would be equal to how many times you saw that array and found T1, and how many times you saw and found T2, and so on, right? Because if you do not look inside that array, if you do not peek inside it, and if you simply swap it down to the children, then you are not really doing any work. So the actual work is done when you are looking inside each of these elements and then partitioning it into smaller buckets. And then when you do it in the smaller buckets, the m that you assign would be the LCM. So let's look at this TI. How many times will we actually look at TI? The first time we look at TI, m was 1. But the next time we look at TI, m would become at least 2. And then for some time we won't look at TI because whatever D that we are encountering, that is being divisible by, that divides LCM. So we do not look at T1 for a lot of time. But then suddenly we look at inside that array and we find T1. So this means that the next time we see T1, the LCM would be at least 4, and then the next time we see it, the LCM would be at least 8, and so on. So it means that after you have seen T1 60 times, the LCM would become greater than 10 to the power 18. This means that after 60 steps, you will never ever see T1 again unless it is a leaf node. So this means that any node, any query can only be seen up to log 10 to the power 18 times, right? Which is roughly 60. Is it? Yeah, it should be roughly 60. So this means that the total amount of work that we are doing is only when we see a query, right? So the total time complexity becomes n into log 10 to the power 18. So that's why you can see that our hoping strategy, right, where we just hope that we got lucky, that is actually correct. We will actually get lucky most of the time, because otherwise if you are getting unlucky, then m doubles, because we have to encode the information that it is divisible in this world and divisible in this world as well. So it should be divisible in both the worlds. But if it is divisible in both the worlds, then the world is growing. And if the world grows beyond 10 to the power 18, then all the elements, no two elements can be equal unless they are actually equal. And if they are actually equal, no need to peek inside the bucket. So now let's look at the code for this. So first of all, you want to find out the LCM between two integers. Now, of course, you want to make sure that you do not calculate infinite LCM, right? So you define a capped LCM function which takes two integers a and b. And if their LCM is exceeding 10 to the power 18, it just returns 10 to the power 18 plus 1, infinity. And this is just the concept of infinity. Otherwise, you use the famous formula that GCD into LCM is equal to product, right? So the LCM is nothing but product by GCD. And we don't know how to actually compute LCM, but we are very well versed with how to compute GCD. So that's why you compute GCD and you like divide it by the product, and that would give you the LCM, right? So this is where you divide it by the GCD. So this way you can compute the LCM of A and B. And now, so this is just this is the final code, and you'll see why it's just a couple of lines of code, but encodes a lot of information, just like that LCM trick. So you see that if it is a leaf node, then of course you don't have to do anything, and you have found your answer. Otherwise, you propagate that buckets around. Along with the buckets, you maintain in what world all the elements of the bucket are equal. But this M smartly encodes all the smaller worlds that we have seen so far. It is encoded in this M. So if the bucket is empty, of course you don't do anything. And then if you are lucky, then the bucket that you just received, that can be simply transferred to one of the child. And when can that be done? That can only be done if all the elements are equal in the bigger world. Then if you pick a divisor, in that world also all the elements will actually be equal. That in that case, or in the other case where if your LCM exceeds 10 to the power 18, but if you still have a bucket with n elements, and we said that AI modulo 10 to the power 18 is actually AI. Why? Because all the elements are less than 10 to the power 18. So this means that all the elements in the bucket are actually equal. So you just transfer that entire bucket to whatever the destination it needs to be. And what is this quantity? So this is the starting time. And we know that what will be the time when you arrive at this vertex? That will be simply, that is uniquely determined if you have the starting time. So this will be M, or basically Ti plus distance of you, and all the buckets will go into this children directly. So you don't peek inside that bucket, you simply transfer it. Now what about the case where we get unlucky? So if we are unlucky, it's no big deal, right? We know that all the elements in one bucket, all the elements in this bucket, they were equal to each other in the world of M. So we iterate over each bucket, and then we partition them based upon what is their modulo in this world, in this smaller world, which does not divides D. And once we have partitioned that, then each bucket will go to a unique child, right? And then we send it to that child, and here we are just doing a brute force. We are just iterating over all the elements, and then we have some arguments to show that this kind of scenario will not happen a lot of time, because uh, we are maximizing the probability that we don't actually peek inside that element of the bucket. So yeah, that was about it. So as you can see, the code is so simple, right? But the logic maybe not so much. But I still believe that it's a good exercise to learn about congruence relations and offline processing on trees. No matter if you implement the brute force version or the optimized version after understanding the LCM concept. But either way, like a lot of people are actually very surprised when LCM and GCD suddenly show up in these kind of problems. But once you do a good number of these kind of problems, you will realize that they are actually expected to show up because modulo deals with multiples, and congruence also deals with multiples, remainders, etc. So these concepts are very interrelated. So do solve this problem and let me know if you have any comments or questions. Let me know in the comment section in the YouTube. I will link down the problem description in the YouTube description. Thank you.